where we left off last time, which is the view of frequency up conversion and frequency down conversion that makes use of those orthonormal functions, right? Those G functions that we have defined in the course. So that is where I want to start today. I want to emphasize that this is a very powerful and also mathematically a very elegant topic. And it has a lot of generalizations, maybe some of it which we will see in the course of this semester before it concludes. Right, so what we have said is that the frequency upconversion process which happens at the transmitter can be thought of as a generalized way of that constellation diagram that we had studied. Essentially, the x and the y axis of the constellation diagram are these vectors g1 and g2. And we have seen that there are several requirements on these functions, g functions. They have to be unit energy in some sense over a period of a symbol, maybe. If you measure their energy, we would like them to be having unit energy. It is not a very essential requirement, but it is useful because if you have these G functions as unit energy, then we can use our definition of the symbol energy that we had studied earlier, which is nothing but the squared distance of the constellation point from the origin of that two-dimensional plane. If these G functions are defined so that they don't have unit energy over a symbol duration, then that symbol energy definition E of S gets a little bit more complicated. And so it's more of a kind of a, it kind of simplifies our mathematics. The first requirement that these G functions have unit energy. The other definition is that, the other requirement on the G functions that we have specified earlier is that they should be orthogonal to each other. Meaning that if I take dot product of these two G functions, it should be 0. And that also is not an absolutely essential requirement, but it again simplifies the life for us. See, what happens is when they have dot product of 0, we can draw them as perpendicular vectors that are at 90 degrees with respect to each other. And with that, we can kind of bring in our traditional x-axis and y-axis as a way to represent these functions g1 and g2. If the dot product between g1 and g2 is not 0, then those two x's will not be perpendicular. So we won't be able to really call them as x and y anymore. But we can still operate. Nothing fundamentally breaks, but the mathematics becomes more complicated. And so these are the two requirements which kind of simplify our understanding and our conceptual analysis. And then with that, we can write the transmitted upconverted signal as linear superposition of the columns of this matrix G, which is made up of these two functions, G1 and G2. Right? So that is how we can interpret the transmitted frequency upconverted signal. We are kind of making use of linear algebra, linear superposition of the columns of the matrix. When you multiply a matrix with a product is a very common way to understand what is going on when you do this matrix vector product. And so in this case, we are generating the signal, the electromagnetic waveform, by combining these two EM waves, G1 and G2, in a specific manner. And that combination is defined by this vectorial coordinates, SM1 and SM2, which specify the constellation point. And we can think of this also as a synthesis operation. We are kind of synthesizing the transmitted modulated signal. Now, at the receiver, what we can say is that the absence of noise, if I take the transpose of this G matrix and multiply with R, then because this G is an orthonormal matrix, we have seen earlier that its transpose is actually its inverse. And so it kind of cancels out and we get the original vector S of M, which is our constellation point back. And this operation can be thought of as inner product operation. We are taking G1 and taking its inner product with the received signal. Similarly, we are taking inner product of G2 with the received signal. And as a result, what we get is the original transmitted constellation point in the absence of noise. And this algebraic operation can also be thought of as an analysis function. So that is what we are going to start looking at now. It's the exact same concept. There is nothing new here that we are going to do now. But because, as I said, this concept is very elegant, very powerful, and in a way, it is actually very easy to understand also. Once you kind of get your arms around it, to facilitate your understanding, I thought I'll draw some diagrams that will kind of help you appreciate this mathematics in a more system architecture viewpoint. You know, this is how we would draw the block diagram of our communication transmitter as it relates to the frequency upconversion, or communication receiver which does the frequency downconversion. Okay, so the frequency upconverter can be thought of as this block diagram. Okay, so I'm now generalizing the modulation to be k-dimensional. Capital K is the number of dimensions. All the modulation schemes that we have seen so far are two-dimensional. So capital K is just equal to 2. And all you need is G1 and G2. But in general, it doesn't have to be two-dimensional. It can be any arbitrary number of dimensions. Basically, it can have x-axis, y-axis, z-axis, maybe one more axis which is perpendicular to all these three, and so on. And so then we get this type of diagram. So what is going on here is that we take this G1 signal and multiply by the x coordinate of our constellation point. We take G2, which is the y-axis, and multiply it by the y coordinate of the constellation point, and then we just add the signals up together. And it can be compactly represented as this matrix vector multiply. So the two equivalent viewpoints are that we are kind of linearly combining or linearly adding or linearly superposing these column vectors, which are this G1t, G2t, etc. These are, remember, the electromagnetic waves oscillating at certain radio frequency. Or it can be thought of as that we are synthesizing the signal S of t. So we can think of it as synthesis of this S of t. Jamie, you want to probably mute yourself? Your microphone is on. Jamie, are you there? Or are you walked off? There's some it's like he's busy watching some movie or something. Okay. Let us see what to do here. Okay, I don't know how to mute Jamin from my side, but maybe he has muted himself now. Okay, so so these are the two equivalent viewpoints of the transmitter. And the good thing is that we are kind of leveraging just the linear algebra here. And that is how we are looking at the modulation operation as it happens at the transmitter side. Now, it is useful for us if we consider even the noise as essentially this noise that the transmitted signal experiences n of t. It is useful for us if we can represent even the noise as some coefficients n1, n2 up to n of k after they get combined with this g functions. So in case of let's say QPSK or 8PSK or 16 form, as you know, these are two-dimensional modulation. So it is only going to be these two noise parameters, n1 and n2. n1 will get multiplied with cosine of 2 pi fct. n2 will get multiplied by sine of 2 pi carrier frequency times t. And then n of t is going to be the summation of the two. Now, sorry, one thing I should add here is that, yeah, so the actual signal, the noise signal, may have some other component present also, right? So for QPSK, in addition to the noise being just a linear combination of cosine and sine, maybe there are some other components present. And so those components of the noise, we are lumping them into this U of t, right? So how to think of it is that the noise doesn't have any finite number of dimensions. Generally, noise is present in all the dimensions. So let's say this is the dimension corresponding to G1. This is the dimension corresponding to G2. And let's say that this is a particular noise realization here, whose x coordinate is n1 and y coordinate is n2. However, the actual noise that the signal experiences may reside in other dimensions, maybe some z-axis, let's say. And maybe 4 dimensions or 5 dimensions. So basically what we get through the additive noise channel is a combination of this linear superposition of the n1, n2 coordinates, plus this additional component which resides in dimensions outside of this. So you can say that this is this vector here is G mod n, right? It is n1 times G1t, n2 times G2t. So that is this vector. But then there is this other vector, let us say u of t. I'm just considering for the sake of simplicity this signal u of t only to be along z-axis. In reality, it will be in the fourth dimension, in the fifth dimension, which I don't know how to draw here. So therefore, I'm taking a simple way out and thinking of u of t as on the third dimension. So maybe it looks like this as a vector. And so what you end up getting as the actual n of t is going to be addition of these two vectors, u of t and this g mod n. So you get some vector like this. So this is the actual n of t. So what I'm saying is that the noise signal may reside in higher dimensional space compared to the space of the modulated signal. For two-dimensional modulation, the modulated signal is confined to be in this two-dimensional space, x and y coordinate. The actual incoming noise may have more dimensions than that. To fully represent n of t, we may need maybe 100 dimensions, maybe 200 dimensions. And so all the remaining dimensions are captured by this u of t. What u of t doesn't have is any component which is in this x and y, g1 and g2 dimension. Because everything that is present in this x and y dimension is already captured by this n1 and n2. So the composite signal u of t is living in dimensions that are other than those covered by g1t, g2t up to g of kt. As you can see here, this u of t is in the third dimension. It is not in x and y dimension. It is perpendicular to both x and y. So this is how we will represent the noise. Does this make sense? Anybody has any question here?
Sir, can you give an example of Z dimension for G1 and G2 to be sinusoidal waves?
Yeah. I mean, one example is that let us take the binary frequency shift keying modulation that we had studied, in which case G1 is oscillating at frequency F1, G2 is oscillating at frequency F2. The noise might be having components from frequency F3, frequency F4, frequency F5, maybe up to 100 frequencies. But all of those other frequencies are orthogonal. They are 90 degrees from F1 and F2. And so those other dimensions are captured by this u of t. Think of u of t as being perpendicular to the x and y axis which cover the modulated signals. Think of the modulated signal as being a constellation point in a two-dimensional plane. So if that plane is like this, then this g of t is like this. It's perpendicular to, sorry, u of t. The additional part of the noise, which is not present in this two-dimensional plane, has to be perpendicular to it. Okay, so that is the general idea here.
Sir,
It's okay. I mean,
sir, I
yeah.
understood that higher dimensions in binary frequency shifting, but sir, I am not able to visualize the in case of G1 is sine of x and G2 is cos of.
Yeah. So again, for QPSK, let's say it is cosine of 2 pi ft. G2 is sine of 2 pi ft. And we have said that those two make up x and y axis. They are perpendicular signals in some sense. Now, compared to those two signals, you can come up with other signals which are orthogonal to these two signals. One way to define orthogonal signals to cosine and sine would be cosine and sine at some other frequency. And you can prove that those other cosine and sine, those other electromagnetic waves oscillating at some other frequency, they will be perpendicular to this cosine and sine.
But sir, we are only considering binary phase shift key. So
Yeah.
how can we vary frequency in that?
No, we are not considering binary phase shift. We are considering two-dimensional modulation. It can be BPSK, it can be BFSK, it can be QPSK, it can be 8 PSK, 16 PSK, 16 QAM, 32 QAM, 256 QAM. All of these modulation schemes are two-dimensional. So I'm saying that for any of this two-dimensional modulation scheme, the frequency upconverted signal lies in a two-dimensional place, two-dimensional space, two-dimensional plane that is covered by G1 and G2. Because that is how we have defined the modulated signal. All it needs is G1 and G2 along with the coordinates by which we weight these two signals. It doesn't need any other dimension. In case of this several two-dimensional modulation schemes that I just gave a list of, I just need two dimensions. I just need cosine and sine, and they form x and y axis. And then using those two dimensions, I am able to generate any of those modulation symbols, any of those constellation points, because all the constellation points are specified over this two-dimensional plane, right? And that is why I say that my transmitted modulated signal at radio frequency is a two-dimensional signal. It just needs two dimensions. Or in general, it needs only capital K dimensions. Why can I say that? Because that is my design. That is how I am generating. That is how I am synthesizing the modulated signal. And in that synthesis process, I have tied my hands. I have said that I'm going to use only capital K different dimensions. I'm going to use only K dimensional space. So if I think of my generated modulated signal as a vector, that vector is confined to be in that K dimensional space. For QPSK, for 64 QAM, etc., the modulated signal as a vector is confined to be within that two-dimensional plane. It doesn't go outside of it. It cannot. If you linearly superimpose two column vectors, then the sum is going to reside in the plane of those two vectors only. You can't get the sum which is outside of it. So that is the diagram that I had drawn here. Now, unlike the modulated signal which I am designing and which I am transmitting from my hardware, which I have designed, the noise introduced by the channel is the generation of Mother Nature. I don't have any control of it. And so that additive noise, I cannot enforce that it has to reside in just that two-dimensional space. In fact, it may reside for all that I know it may reside in 100-dimensional space. I might need 100 different orthogonal dimensions to be able to reproduce or to be able to synthesize the noise that I see at the receiver. So this n of t, I cannot kind of confine it to the space of the modulated signal. That is what this equation says, that n of t is a linear superposition of one component which resides in the modulated signal space, which resides in that k-dimensional space of the modulated signal. But then it will have other component which is escape out of this k-dimensional space, which are not part of this k-dimensional space. But those other components together make up this u of t, which has to be perpendicular to the space in which the modulated signal is present. Does that help you?
Sir, I am having a doubt over here.
Yeah, go ahead.
Sir, suppose the noise is existing in the channel in all the dimensions, right?
Mm-hmm.
Then the first k components of that noise n1 to nk got that vector got get means we calculate the noise by the product of that noise vector with this GS because due to the frequency upconversion, right? Means means this means during the upconversion of the signals, the noise also got upconverted.
Well, nobody upconverts the noise, right? But
yes, but here we see that
but what I'm
it is
saying is that when you are transmitting your modulated signal at some carrier frequency f of c, let's say f of c is 5 megahertz,
yes.
and so that signal got sent out by the transmitter. And what you will see is at the receiver, what you will get is not that exact signal. It will be the signal plus some noise. So how to think of the noise that got added by the channel? Well, you can say that part of the noise which got added by the channel is the cosine and sine, the EM waves at 5 megahertz. The strength of those EM waves is specified by N1 and N2. Why can why should I think like that? Because, you know, we don't realize it because we can't see the EM waves, but EM waves of all the frequencies are always present in the atmosphere. We can see only the visible portion of that spectrum, but other components are also present. And so if I'm transmitting cosine and sine at 5 megahertz from just the environment, there'll be additional component of cosine and sine which will kind of mess up my transmission. They will get added to the transmitted signal. But in addition to just those cosine and sine oscillating at 5 megahertz, I will have a lot of other noise also present in the incoming signal. And that is what I have captured here as U of t.
And sir, is there a way to measure the noise in higher dimensions?
That we will talk about later. Okay. For the time being,
Okay.
you just take it here that the noise which is present in the environment and which the receiver observes, it will have some component which is along x-axis, some component which is along y-axis, and a whole lot of other components which are along the perpendicular dimensions.
Yes, sir. Now I am getting it. Yes, sir. Thank you. Thank you, sir.
And so I can now draw a block diagram of the received signal, R of t. This part is what we saw 2 slides ago. This is the synthesis operation at the modulator. here is where I'm generating or I'm synthesizing the modulated signal. At frequency upconverter. This is how we are representing the noise. It has some component which is present along the k-dimensional space of modulated signal, and it has maybe other components which are perpendicular to it. So n of t is, again, I forgot to add u of t part here. And that is what my r of t is. R of t is the transmitted signal s of t plus the noise signal n of t. Okay, so that has made us reach the input to the receiver. Now let us see what the receiver looks like, or specifically the frequency down conversion at the receiver, how it looks like. And so if you recall from several lectures back, we had defined that the dot product between these two signals, R of t, which is our received signal, and any particular g functions, let's say g1 of t. These are time domain signals. They are actually not vectors, but still we can think of a dot product, vector dot product operation between these two as this integral from 0 to symbol duration t sim. The product of rt and g of t gives us the dot product. So that is shown by this block diagram. We take the incoming signal r of t, we multiply by g of t, and then we integrate over symbol duration, t sim. This capital T should have been t sim. So this is the block diagram representation of the receiver. And basically the receiver takes the incoming signal and it projects that signal. And by the way, if I think of this operation as the vector dot product, then this is now not linear superposition anymore. This is called the projection operation. So I'm taking R of t and I'm projecting it along each one of G1 of t, G2 of t, and so on. And that projection operation or the dot product operation gives me a scalar, which are this R1, R2, R of k. So again, there are 2 points. One is that we are projecting R of t onto the each of this G1 of t, G2 of t, and so on. Or this is called the analysis of the received signal. We are taking R of t and we are analyzing it to see what it is made up of. R1, R2, R of k.
Sir,
Yes.
sir, when we do this integral as we can think of as vector dot product, then all higher dimensional noises u of t will be vanished, right, sir?
That is very good point. So that is, I think, my slide. Oh, by the way, yeah. So Vandan, what you said is correct, and maybe I will have a slide on that. But before we get there, what I want to show is that suppose there is no noise present. Okay, I mean, consider an ideal environment. There is no noise at all. It's a kind of fictitious case, but nothing prevents us to think of such a situation. Then this is how the overall system will look like. The transmitted signal is given by linear superposition of this g functions, and at the receiver I am doing this projection operation. This here on the left hand side is the upconversion, frequency upconversion. This is the frequency down conversion. And in the absence of noise, it turns out that this individual R1, R2 are nothing but the transmitted constellation coordinates, SM1, SM2, and so on. This is how it happens. And who can tell me why this has to be the case?
Because dot product of all other dimensions is 0 with respect to particular dimension.
Yes. So if I consider this output vector, output coordinates as a vector R, right? R1, R2, R of k, then they can be thought of as this G mode transpose function. We are applying that on the received signal, which is in this case S of t, because there is no noise. But S of t, here it is already written as G mode times S of m. So it turns out to be G mode transpose t times G mode t times S of m. But this, as we have seen earlier, is an identity matrix, and so we simply get S of m back. Essentially, this is happening because each of these EM waves, we have defined them to be unit energy and orthogonal to each other. Okay, now the next thing is that in the presence of noise, one thing we can say, like I think what Vandan has mentioned already before, one thing we can say is that in the presence of noise, at least, this U of t has no effect on what R1, R2 up to R of k are going to be like. You can dump a whole lot of U of t at the receiver, or you can just wipe them out. Maybe in one case U of t is 0, there is no U of t present. In the other case, U of t is present a lot, maybe in a very high powered manner. What will happen is that in both the cases, this R will be exactly the same. So the way to see that mathematically is that, see, the receiver is doing G mode transpose of the R of t. So if I do G mode transpose R of t, this is same as G mode transpose S of t plus G mode t of n vector plus U of t. Now, if I look at the third term of this, if I open up this bracket and if I just look at the third term is going to be, so there'll be first term, some first term, this G mode t plus S of t, second term, which is G mode transpose G mode n, and the third term will be G mode transpose of t U of t. And it is this third term which is going to be 0, no matter what U of t is. The reason it is going to be 0 is because U of t is perpendicular to each of this G1, G2, Gk. And whenever we are dealing with a dot product of two perpendicular signals, you get 0 at the output. Okay, so we introduced this U of t only to say a few slides later that it doesn't matter. But still, I wanted to introduce this additional component U of t, because with this, I hope you have got the idea that any arbitrary signal, if you generate noise randomly, completely randomly, which is what happens in the real life, then that generated noisy signal, you can't confine it to just 2 dimensions or 3 dimensions or capital K dimensions. It will have energy present in many, many dimensions. However, the nice thing about the receiver which does this dot product operation along G1, G2, etc. The nice thing about such a receiver is that the energy of the noise which is present in the dimensions other than the ones that you have designed at the transmitter doesn't matter. The reason it doesn't matter comes out from just our linear algebra concept. So here we are kind of applying some of the linear algebra concept that you would have studied in your high school math. So what is going on here is that, like what we said here, that this G mode transpose, which is the down conversion operation at the receiver, and G mode, which is the up conversion at the transmitter, they are inverse functions of each other. So they cancel out. And so effectively, I can draw a red colored tape around this entire block, which includes G1, G2 at the transmitter and at the receiver. And I can say that all of it kind of, in ideal sense, it collapses. And so all that we get is a simplified model of the modulation, which looks like this. But this is exactly the model that we had studied earlier. One that we called simplified model, the one that you did in your lab 8 in the first week. There was no frequency up conversion, down conversion. So the effect of frequency up conversion and frequency down conversion, if the transmitter and receiver are working properly, kind of cancels out. So in that case, what do you think? Why do we want to even do frequency up conversion, down conversion? If ultimately it cancels out, then why to even think of doing it? If you suppose have I don't know, 100 rupees with you, and you have to give, let's say, 50 rupees to your friend today, and 5 minutes later, your friend gives you back that 50 rupees, then you got 100 rupees back. What's the point of giving the money to your friend and getting it back? It's a bad analogy, not a good one, but still, I hope you get the idea. What is the reason to do frequency up conversion, frequency down conversion? If ultimately, at least mathematically, we have shown that it kind of cancels out.
Sir, can I answer this
Sir,
question?
energy efficiency.
Size of antenna
travels longer distance with smaller antenna if RF band.
Yeah, so that is one reason that the signal, if you just transmit this SM1, SM2, the coordinates of the constellation point, it's going to be difficult for you to use antennas, which are practical in size.
The size of antenna decreases.
And the second reason is that using this electromagnetic waves, we can position our signal spectrum anywhere we want in the RF along the radio frequency axis. So that allows us to do some sort of channelization. Okay, so although I want to emphasize to you that frequency up conversion and frequency down conversion are inverse functions of each other, I don't want to trivialize it. They are very much required. So last thing we are going to do, I think this is an exercise that I'm sure you can do yourself, but we will plug in some equations and see actually what is going on at the receiver. So maybe let me just first give you the simpler version. So this is for a two-dimensional scheme. The transmitted signal is given as this equation. It is linear superposition of the in-phase and the quadrature EM waves. You know, GI and GQ are cosine and sine. This we have called G1 and G2 also before. And this SI and SQ are the coordinates of the 2D modulation constellation symbol. And so at the receiver, so this is our RF signal. It is upconverted to radio frequency. And this is what the receiver gets. Now, the way the receiver will extract, given S of t, given this signal S of t, the way the receiver will extract S of I is it will just do the projection. It will do the dot product of S of t with G of I of t. This is the first part here that we had seen. This is how it is going to get S of I. Now we are going to mathematically prove that that dot product is indeed going to give them S of I. So let us see what this dot product turns out to be. If I plug in the equation for S of t from here, and then just expand the brackets, the first term becomes S of I gi squared dt. And the second term becomes S of q gi gq dt. All that I did was I took for this S of t this equation. But individual GIs are unit energy and they are orthogonal. And so this term here will become 0 because of orthogonality. And this term GI squared part will become 1. And so you just get S of I. And same way you can show that you can get S of q if you do 0 to t sim integration over t sim S of t g q of t. What you are going to get is S of q. This is the simpler way to see what is going on in those block diagrams that we had seen. Now, the same math, exactly the same math, is what I have written here in a more detailed manner. So S of t is Si times this is G of it, remember? This is G of qt. This bracket here. And I'm going to again do the same operation as what we had seen symbolically before. S of t times G of it. So if I expand it out, it looks like this. But this cosine of square, I can write it as 1/2 of 1 minus cosine of 4 pi fc. And this product cosine sine, I can write it as 1/2 of sine of 4 pi fc. So I bring different terms in different integrals. So I get this first integral, second integral, and the third integral. Turns out that these two integrals are actually zero. If not exactly zero, they are pretty much zero, approximately zero. All that remains is this first integral whose value is s of I. Okay, so this is like a mathematical proof of those block diagrams that we had drawn. Last thing I want to mention before we conclude is that the assumption is that receiver can on its own generate G1 of t and G2 of t, or Gi and Gq, which are exactly matching with Gi and Gq used by the transmitter. That is the problem, that in reality, the receiver will have some phase error. Gi and G2 will not be exactly Gi and Gq of the transmitter. There will be some unknown phase error. Hopefully it will be small, but it will be there. So what happens if you do the same operation as here, but instead of the receiver having exactly cosine of 2 pi f ct, you have cosine of 2 pi f ct plus some phase error. Then I'm asking you, you go through this math and tell me what is the problem if that phase error is present. Okay, so that is where we are going to complete this topic of frequency upconversion and downconversion. We have about 15 minutes left, so I'm going to take a very quick break, and then I'm going to, for the remaining part of today's lecture, I want to kind of generalize this analysis and synthesis methodology. Okay, I want to kind of, I want you to think about this synthesis and analysis functions in a more general way. So that is what we are going to try and do after we come out and finish this quick break. Okay, so are you able to see my screen?
Yes, sir.
Okay, so I have a MATLAB live editor, and I want to talk about a generalized scheme for this orthonormal or orthogonal matrices. Okay, so far we have seen that this G mode matrix has two columns, maybe cosine of some frequency and sine of some frequency. We say it can have many more columns, maybe cosine of frequency 1, cosine of frequency 2, cosine of frequency 3, so on, up to capital K different columns, which are those K perpendicular axes. And in context of frequency upconversion and downconversion, we have been thinking of these signals as electromagnetic waves, which are kind of continuous in time. They are analog signals. Now, a lot of the times, in a wider sense, maybe in context of machine learning, in context of signal processing, signal analysis, in context of big data analytics, in a lot of domains which are not necessarily communication theoretic domains, but also in communication theory as well. The signal that we get or the data that we have is already discretized in time. We have different samples, we have different data points, right? I mean, if you're generating some data in Excel or in Google spreadsheet, then those are not continuous in nature. Each row has one value, and so these rows are You can think of them as different samples. And so for such cases, that G mode matrix actually becomes a real matrix. It will be having different columns and different number of rows. And so one type of such a matrix is what we are going to look at now. It is called the discrete Fourier transform matrix. And it has total of capital N samples where N is some variable. So that N is what I have made here to be a variable. Maybe let me make it N to be 64, meaning there are 64 data points. So now with those data points, with N samples, we are going to define a time variable, which will go from 0 to N minus 1. So this will have total of N samples. You can think of them as the index of the row of your spreadsheet. N is nothing but a timestamp. Now, this part is something new. We are going to define a frequency variable that we are going to call small k. And this frequency variable will also take total of N different values. But for the sake of simplicity, we are going to normalize them by N. So this frequency variable, the time goes from 0 to N minus 1. Frequency will go from 0 to 1 minus 1 over N. It's a fractional value. By the way, are you able to see what I'm typing? The letters here, all of these are sufficiently of big size for you to see them?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Okay. And so now I'm going to define this G matrix as an exponential function which will have complex argument. 1i is square root of minus 1. 2 pi times frequency times time. But the specific way in which I have defined the frequency, which is a column vector, and the time, which is a row vector, when I multiply k times n, I get a matrix. Because k is n cross 1, n is 1 cross n. So I get k times n, which is n cross n. So I'll get total of n cross n values, and then I multiply them by 2 pi, multiply them by square root of minus 1, and then take exponential function. So I'm going to get some n times n matrix. Now, quite intentionally, I have made it to be, I have denoted it as G matrix, kind of in line with our earlier notation. So first of all, let us see what different columns of this G matrix looks like. So I'm now going to first select the very first column, right? And the column selected is 1. For that, see, column is going to be all the values of k from 0 to pretty much 1. As n becomes large, k goes from 0 to 1. 1 over n tends to become 0. So for each column, k will be the same. But the behavior of the column will be dictated by that particular value of n. When I select the first column, the very first value of n is 0. So this first column of G is going to be exponential of 1i times 2 pi times k times 0. But then it means that all of these values are going to become 0. What happens if you take exponential of 1i times 0? What do you get?
1.
1.
You get 1. I'm going to plot both the real part and the imaginary part. Real part is going to be the sign, right? I mean, if I expand this complex exponential, I can also write it as cosine of 2 pi kn plus square root of -1 times sine of 2 pi kn. So maybe I will write it here specifically. G can, I can also define the same function, exactly the same function. This is our definition of complex exponential. Cosine of 2 pi kn, sine of 2 pi kn. So when this n is 0, this sine is going to be all throughout 0, whereas this cos is going to be all throughout 1. So the very first column of this G matrix is going to look like this. The real part is constant 1, imaginary part is 0. So it's a DC signal. It's a direct current, constant value, no changes. Okay, if I go to the second column, what do I get? I get a nice cosine, which is the blue, and a sine, which is the red. And they complete exactly one cycle over this capital N samples. Why do they complete one cycle? Because I'm going to the, essentially I am kind of taking a signal whose frequency is 1 unit. If I go to the third row, I again get the same cosine and sine, but they complete 2 cycles over this time sample. By the way, I think another way to see the same thing is instead of column select, I can do row select, and you'll see nothing changes. This G matrix that we have defined in this way is pretty symmetric. I can make column to be rows and rows to be column. And apart from some complex conjugation, nothing much changes. So do the same thing. So on the third row, I get the same type of signal, except it is oscillating 2 times. So if I select the third row, I'm going to the third value of k for all values of n. If I select the fourth row, and I have incremented my frequency variable k, small k, by 1, which means that instead of completing 2 cycles, now the signal will complete 3 cycles. So this is completing 3 cycles. If I go to 8th row, then it will do 8 cycles over the 64 samples. Okay. That is the nature of this G matrix. Now, turns out that this G is an orthogonal matrix. Okay, it's not orthonormal yet because I have not normalized the energy of all of this column vectors. In fact, the energy of each of these column vectors is going to be n. But different columns of G are going to be orthogonal to each other. So that is the part which we are checking here. if I do G transpose G or G transpose, in either case, I get an identity matrix. Only the diagonal values are equal to n. All the cross diagonal values are zeroed out. This is the standard definition of a matrix whose columns are 90 degrees apart from each other. Right? So this is a way to generate the G matrix in a generalized manner. And this is actually, turns out that it gives us the Fourier transformation. In the Fourier transformation, what we do is, using this G matrix, we can synthesize a signal. Remember the synthesis and analysis? So what we are going to do is, first we are going to synthesize a signal. It's a time domain signal that we are going to make up. And the way we are going to make up is by combining the first frequency, second frequency, third frequency, and the fifth frequency. Okay. And so these are the 4 frequencies that I'm selecting. And at those locations, at the selected columns, I'm going to specify the weights. So the first frequency, I'm going to weight it by 0.5. Second by 0.8. Third, I will give it more amplification. I will give it a value of 2. I will multiply the third frequency by, I will double it in amplitude. In the fourth frequency, I will multiply by 1.5. So this is going to be my synthesis operation. This is how I'm combining different colors, so to speak. I also have this exponential term. These terms are going to just allow me to randomly change the phase of each of these frequencies. I don't have to change the phase. I can make all of the phase to be 0. But for generality, I said that, okay, I'll just randomly put some phase weighting also. So what are these weighting coefficients? So let us plot them. You see the first one is 0.5. Second one is 0.8. This is at 0.8. Third one is 2. Fourth one is 0. Right? I haven't selected the fourth one. And then the fifth has a weight of 1.5. And then all the other remaining 64 frequencies, I am not even using. I have those colors with me, but I am not going to make use of them. What does a time domain signal look like, which has this type of frequency components, this type of weighting? By the way, these are the phase values, okay? Because I generated some random phase. But the point is that the phase for all the other frequencies are 0 because we are not even using them. This is our synthesis operation that we just now looked at in the context of modulation upconversion. S of f is this vector that I have specified, which I have plotted here. And I'm just I'm taking G multiplied by S of f. And this is going to give me the synthesis part. It is going to linearly superimpose column number 1, 2, 3, and 5 of this G matrix, except before adding, I will take the first column, multiply by 0.5 times some phase, second column by 0.8 times some phase, and so on. And so now, what will the resulting synthesized signal look like? So that we can see here. This is how it looks like. In general, it will be a complex signal. It will have real part and imaginary part. And this is how it turned out to be. Pretty interesting. I got a strange looking signal, which is some combination of the first, second, third, and fifth frequencies of that DFT matrix. And the last thing that we will do is we will analyze this signal. Now, suppose that we are given this signal in the laboratory. We don't know where it came from. We are just given this S of t. We want to know which frequencies are present. Then we will do G transpose of this S of t. This is our receiver down conversion operation. In the context of this G matrix, this is called the Fourier transform. It's an analysis function. And so we will take that S of t, which is plotted here, and we'll pass it through the analyzer to see what frequency component are present. And you see here, I got first frequency at 0.5, 0.8, 2, 1.5, all the others are zeros. So even though in this case, I kind of closed my eyes and I said, okay, I don't know what this S of t is made up of. This analysis function told me that it is made up of these 4 frequencies with this type of weighting, which exactly matches how I generated S of t in the first place. So what we did here in this section is called analysis, but it's actually the Fourier transformation. What we did here is called the synthesis, and it's also called the inverse Fourier transformation. Okay, so this is a very quick